used to take one-day trips to Manhattan and stuff like that. But anyways, it was a little blast from the past. So I do a lot of work with microservices and service-based architecture, and also service-oriented architecture, and also reactive. And had a couple of topics to talk about. And at first, Scott and I thought, oh, maybe the microservices stuff would kind of be interesting. But if you're not currently using microservices, then it's kind of out of context. And we thought this is a little bit more general for a Java user group. So before kind of going on to my spiel, there's just kind of a couple of things. First, Jay Zimmerman from NFJS, No Fluff Just Stuff, is sponsoring me for being here. And I just wanted to let you know, we do have the Great Lakes Software Symposium coming up October 14th through 16th here. And if you've never attended an NFJS show, they're really awesome. Hour and a half long deep dive sessions, excellent speakers, it's a lot of fun. So anyways, if you type in the code NFJS user group 50, you can get a $50 discount. But also, do we still have the raffle tickets? Does everybody have a ticket? Good, because we're going to raffle off a free pass to Chicago's NFJS conference. So, and if you do win, and you know you're not going to be able to attend, if you know you're not going to be able to give it to a friend, then then let me know and we'll raffle it off again. But do we have a fishbowl with the raffle tickets?
Yeah, coming.
Oh, okay. Oh, I didn't see you around the corner there. Sorry. All right. And I think there's some other swag to give away, but are we going to do that later on? Oh, there's the fishbowl. All right.
Oh, yes.
Fantastic. Okay. Let's see. I probably shouldn't pick this because it's going to be me. All right. Can you read the last three numbers? I don't have my glasses on.
385.
385. 385.
Fendi.
All right, we're a
Fendi.
winner!
All right. Fantastic. All right. So that is on. Let me get, for some reason the Apple TV just kind of went off, but let me get that back here. Oh, that's weird. All I need, if you can write down your name and email address, and we will get you that free pass. So October 14th.
Thank you.
Awesome, fantastic. Okay. All right, let's reconnect here. That was a little weird. And oh, okay, I could not connect. Let me see. No, still on pod. It just kind of went off.
Did you get sleep settings?
No? No, it's not. No, cannot connect. That's weird. It's showing.
NG.
Okay. Hold on one moment while we do this technical difficulty thing. All right. And reconnect. Okay. Oh, that's really weird.
Let me go ahead and type.
All right. Well, actually, I have a lot to say while Jean is figuring out why that's not working. But anyway, so let me actually start. Once that kind of goes back, you let me know when you want me to try it again. In the meantime, my talk is about reactive architecture patterns. I've got a couple of goals basically in this particular talk. The first really is to kind of really have you fully understand what reactive architecture really means. I'm also going to be discussing the differences between reactive architecture and reactive programming and how those two things differ. But more to the point, this talk was really born out of frustration. I got interested in reactive architecture about a little over a year and a half ago when the very first Reactive Manifesto came out, and I just absolutely loved it. And it's just one of those things that caught my passion. Anyways, I started getting a little frustrated when I would read articles and kind of blog posts about, in order to be reactive, you must use Akka. In order to be reactive, you must use Scala and Elm and Play and all these other languages and frameworks. You must be on the cloud in order to do reactive. And this kind of frustrated me because I've been doing reactive for a year and a half before most of these frameworks were kind of out and mainstream. And so one of the things I purposely did here to show you reactive patterns is to just use Java. Now, that doesn't mean that I'm knocking any of the Lightbend type of frameworks or Akka or Scala or any of these. I mean, they're incredibly useful. And I'm actually going to show you where they kind of come into play. But I'm also going to show some of the limitations associated with some of those frameworks. So I just want to be clear that I'm not actually kind of, what's the word, knocking them, but rather showing you that you do not need those frameworks or languages to be reactive in your applications. Try it again. All right. Aha. Oh, a different code. Oops. All right. And we are back. We're back. Okay. Fantastic. All right. So anyways, those were kind of my two goals. And we did raffle that off, so like I said, just need your name and email address. So the other thing I wanted to mention kind of before we actually start talking about these patterns is I do a 3-day software architecture training. As a matter of fact, we just had it in April here in Chicago. And it's a blast. It's 3 days of kind of hands-on architecture. We kind of start at the very beginning, go through all the architecture patterns, component-based thinking. I touch almost a full day on the soft skills of architecture, including teamwork, facilitation, negotiation, all the leadership things of becoming a software architect as well. So kind of also introduce aspects of integration architecture and enterprise architecture in there. And there's a lot of hands-on exercises as well in there. So it's quite a blast. I've done, I guess, about 6 classes so far, 5 or 6 classes. And all of them have been a huge success. So anyways, I'll be in Columbus in September, and then Dallas in October, November in my hometown in Boston, and then in December in Atlanta. So we'll be coming back to Chicago probably next year, around the April timeframe. But if you want to catch any of these ones, there are some spots left on these particular conferences as well. So, or I should say training as well. All right, fantastic. So enough of the fluff, let's get on with the stuff, what we're actually going to talk about. So what I want to do at the very start is really just do a very brief reactive architecture overview, kind of just to kind of set the stage. And in here, I also want to talk about the differences between reactive architecture and reactive programming, because this becomes kind of a confusion in the industry right now. Then I want to go over some patterns. What I'm going to show you in these patterns really is the kind of the construct of the pattern, what it's actually answering or what it's trying to solve from a reactive standpoint. I'm going to use the Reactive Manifesto as a roadmap for these. And then I'm going to show you and demonstrate the problem associated with this particular issue. We're going to look at some code, very simple code just in Java, to how to implement that pattern, and then I'm going to show you the results of that. And we're going to kind of see a lot of interesting things. It's actually a lot of fun. So we're first going to look at the most basic of all patterns, the channel monitor pattern. Next, going to move on to the consumer supervisor pattern, one of the most basic patterns in reactive architecture. Then the producer control flow, kind of one of my favorites because it's actually the most controversial. But then we'll move on to my true favorite, which is the thread delegate pattern. This is an extremely powerful pattern. I'm just going to spend most of my time on this particular pattern here. We'll then move on to, oh, we got a lot to do tonight. The workflow event pattern. Now, just due to timing, I probably won't show the code on this, but I want to show the pattern of this, because what I'm going to do is then combine all of these patterns together to show you an architecture that is highly, highly reactive. Okay? So we'll end with kind of combining those patterns together. Now, I'm going to show you some code on the screen, but then I'm going to be doing a lot of running of code to kind of demonstrate for you a system, my laptop here, which is about to crash, and how we can actually programmatically be reactive. And again, all I'm using is Java and RabbitMQ. And speaking of which, you can get all of the source code I'm actually going to show you on my GitHub repository at WMR513/reactive. And as a matter of fact, the slides are all up there as well. So you can just go to the GitHub repository, you'll see the slides as well as all of the source code I'm going to be showing you and running. Let's see. Yeah, there's nothing actual, you don't need any other frameworks other than just Java. 1.7 minimum. I'm running 1.8 here, but you can certainly run it in 1.7. And most of the code, like I said, is in RabbitMQ, but you can certainly use ActiveMQ if you want to. Just kind of, I'll show you the places to change that code. So anyways, all right, let's get started. So I want to kind of start with an overview. And as a matter of fact, I kind of want to start with this image because my daughter loves to play Sims. Now, Sims is a game from EA, Electronic Arts, where you actually build these sim characters. And you can assign them personalities, height, weight, age, clothing, all kinds of stuff, including their personalities and stuff. And so, anyways, my daughter loves playing this, and I was kind of watching her, kind of behind her, watching the Sims characters all running around the town. And it started to rain in the town. Now, some of the Sims characters looked up and started running for shelter. It was kind of cool. She was just not doing anything. She didn't have her hands on the keyboard at all. Other Sims characters kind of just were talking like Sean and I here and didn't even think it was raining. Others kind of looked up in the sky like, what is that? And I thought it was so cool. And I'm like, wow, I wonder how, oh, I know how they do that. It's all about reactive. And I kind of thought, what a great way to think about reactive, because all these Sims characters are just event processors. And based on their personality, they're reacting to certain events. And I just kind of thought it was really a neat way to describe reactive. So anyways, I kind of wanted to start with that image, but more to the point, we have something called the Reactive Manifesto. Now, it's kind of interesting because, and again, I'm going to talk about reactive architecture versus programming in a bit. But what we have is a call to start creating systems that are more responsive, more resilient, more elastic, and all message-driven to kind of tie this together. Now, those of you who are familiar with the Reactive Manifesto have probably seen this diagram here, but what I want to do is actually kind of just spend a couple of minutes going through it, because we're going to use this as our roadmap when we look at all the patterns of reactive architecture. Okay, the first is responsiveness. So this is where the system responds in a consistent and timely manner whenever possible. In other words, how the system reacts to users. And some of the key points here is rapid and timely manner, but also consistent. And that's going to become very important when we look at one of the reactive patterns we're talking about. All right, next is resiliency. For my water here. Boy, I thought Boston was humid. Whoa, man. All right, I guess you guys have a big lake near you, so it kind of makes sense. Anyways, this is how the system stays responsive after failure, and that could be through delegation, isolation, containment, but really this is how the system reacts to failures. Okay, and so that's the second part there. The third is elastic. In other words, this is how the system stays responsive under varying workload. In other words, how the system reacts to load. And finally, message-driven, which system relies on asynchronous messaging to be able to contain errors, to be able to provide loose coupling, transparency. And it's interesting, if you kind of look at this diagram, it's pretty eye-candy, but those arrows all mean something. We're going to see this when we start to actually look at the patterns. Because if you look at, first of all, let's start with responsiveness. Okay, you'll notice that resiliency and elasticity both point to responsiveness. So in order to be elastic, it also feeds into being responsive. The other thing is that elasticity and resiliency also interconnect. But you'll notice that all three of those things are tied together through being message-driven. Okay. All right, and message-driven, of course, is how the system reacts to events. All right, so now I want to talk a little bit before we start getting on custom coding about reactive architecture versus reactive programming. What is the difference? I have absolutely no idea. So anyways, so let's move on to our first, actually, probably about 6 months ago, that was my answer. I have absolutely no idea, but I've had a lot of conversations with colleagues, folks like Venkat Subramanian, my friends Neil Ford and Scott Davis, and a whole bunch of other colleagues about what is this thing about reactive programming and reactive architecture. And we've been able to come up with two definitions for this. Reactive architecture, although the first is about really scoping. Because when we talk about reactive architecture, it's how our systems react to global events. In other words, external things happening to our particular application or our particular request. Okay, so in other words, the virtual machine is about to run out of JVM. We've run out of threads. We can't process fast enough. You know, these are things, what we're going to be looking at tonight, that are in reactive architecture. So the first piece is about scope, because when we talk about reactive programming, what we're really talking about are all the quadrants that we just looked at in the reactive manifesto, but really it's from a request basis. Like when we talk about resiliency, reactive programming is less concerned about external systems that are failing that we're dependent upon, or even the JVM or even the virtual machine, as opposed to the individual request failing. And so that's one of the differences we've come up with. But there's another one. Because if you think about some of the reactive programming languages and frameworks we have, what it comes down to really is a style. In other words, way back in the day, yep, that's me, we had procedural programming. And then, of course, it went to object-oriented programming. And then, of course, we have functional programming. And now we have reactive programming, which does not necessarily have anything to do with the Reactive Manifesto, but really a style of programming. If you consider something like Angular 2, for example, we code based on subscribers and observables, and this is a style of programming independent of things failing or elastic or any of these kind of things. And so that's another one of the differences associated with reactive architecture versus reactive programming. It still is very confusing though, as you can see, but part of what I want to really enforce in this talk is that those tools, as I was mentioning at the very start, are incredibly important, or I should say useful, but not required to be reactive. So tomorrow morning, you can take all of these patterns that I'm going to be showing you, and you can go back to work in the morning and apply these in your monolithic Java application. Okay, so that's kind of what I wanted to enforce. Now, I am going to be using RabbitMQ. I chose to use that instead of ActiveMQ just because, first of all, I like RabbitMQ a lot better. I like AMQP much more. And secondly, it's kind of gaining in popularity, especially in the microservices space. So I kind of thought I'd stick with RabbitMQ. So I thought it'd be worth kind of, since we're going to be looking at some RabbitMQ code, at least to become familiar with what AMQP is really all about. So let's just spend a minute or two talking about this. All right, so we have a producer and a consumer, kind of the same way we do in any sort of messaging thing. The difference with AMQP, Advanced Message Queuing Protocol, oh, by the way, I kind of forgot. Is anybody here, I'm assuming this is a jug. Good, so I don't need to keep doing MSMQ and .NET assemblies and all that kind of stuff, right? Right, good, okay. So, is anybody here using like ActiveMQ or HornetQ? How about ActiveMQ? Oh, good. Group in the back there. So, if we're communicating consumer to client, what's the underlying protocol that ActiveMQ uses?
Open wire.
Ah, rats. The correct answer is, who cares? Now that's correct, it is open wire, but the point is who cares, because we can, with Java, with JMS, Java Message Service, we can swap out ActiveMQ, and we can put HornetQ in place without changing our code, because it standardizes on the API. What's the underlying protocol for HornetQ? Good, whoever said who cares? You got it, that's right. Because we don't care. However, one of the deficiencies of JMS, Java Message Service, is it's a standard across the Java platform. So if we want to extend messaging to other platforms, we can't. And that's one of the limitations. Now you might say, well, no, you can, because we're using ActiveMQ to be able to go over to MSMQ or .NET. It's because all these vendors have built-in bridges to be able to transfer those protocols. But anytime you do that, something gets lost. So anyways, AMQP standardizes on the wire-level messaging protocol. In other words, this is how the packets are sent back and forth across the wire between you and I. So when I decouple what the message structure looks like, when those packets get sent, when you can reconstruct those. But there is no API. That's why I can use RabbitMQ, and I can communicate with you, and you're a StormMQ, let's say. And it doesn't matter, because the underlying protocol is the same. So we have a producer and a consumer, as you can see here. However, what a producer does is it actually communicates or sends to something called an exchange. And then the consumer sends to something or receives things from queues, listens on queues. You can kind of see producers have no connection with queues whatsoever. So there's obviously a missing link. And that's called a binding. And there can be, as many bindings as you want. There can be a many-to-many, one-to-many, many-to-one relationship. Whoops, there we go, there's the binding. That binds an exchange to a particular queue. So you can kind of see AMQP not only standardizes on platform-independent messaging, but also allows us some sort of routing capability as well. All right, fantastic. Let's get on to the patterns here. So the first one I want to show you is extremely simple, but it's a foundational pattern because we're going to be using this for all the other patterns. It's a channel monitoring pattern. So this asks the question, how can you determine the current load on an event channel without consuming the message? And this, by the way, if we look at the roadmap, is all three quadrants of reactive architecture. It's required for all three. So in other words, if we kind of look at this pattern, here we have an event consumer listening on a channel. And messages come in, and of course they're consumed, but then there might be a whole bunch of other messages. So what we have is an event monitor, which actually is monitoring how many messages do I have. Now, most of the time, if you got system errors or something like this, you'll have the, Net Dynamics, Net Dynamics or Coradiant or New Relic, all these beautiful eye candy screens up on the monitor. It's like, uh-oh, our systems are going down. Hello, John? Yep. Yeah, it looks like we're redlining on all these. Can you start up a couple new servers? Hello, John? John? Oh, there you are. Yeah. Can you, never mind. They're down. That's not reactive. So, what we're talking about is doing this from a programmatic standpoint. So, what I'm going to do is put this here. Hopefully everybody can still hear me okay. I'll move this a little closer. Okay, cool. So I want to show you kind of the basic setup. This gives me an opportunity to actually show you the places in the code when you want to run all these examples that you'll need to change. Okay, so let's move over here. First of all, if you go into the source code inside my GitHub repository, there's two things you need to be concerned about. You'll see a README. Whoops, I want to get that a little closer. There's anything that starts with capital AMQP is mine. And so that's code that I'm actually going to be running. But there's two things that you need to be concerned about. One is AMQP common. And the point is here, what I'm doing is I've got a connect method that I've coded myself. So when I'm showing you all the other source code, we don't have to go through all this kind of crap every single solitary time. In other words, I just consolidated all this. So you're going to see amqpcommon.connect. And what that does is it creates a connection factory. It sets the host. You will need to set your own host, obviously, and you'll need to set your own port. Those are the two things that you need to change in the code to get this running. Okay? And then it creates a new factory, a new connection, and returns that channel. All right. And then the close just simply does a connection close. All right, and by the way, I am running, let me show you here, I am running Docker, basically Pivotal's latest RabbitMQ. You can run this natively, or you can just get the latest Docker image. And all this information is right here in Docker. So if you just do a Docker PS, for example, you'll get that actual port number. All right, fantastic. And the other thing you'll need to do is run this AMQP initialize. And this is what sets up and declares all the queues, all the bindings, and all of the exchanges. All right, fantastic. So let's go look at the issue here. And I'm going to show you what we're going to be doing is we're going to be buying a lot of Apple stock. I should change this to Peapod. Do you remember what your, I should have thought about that ahead of time. I was on the plane and just kind of goofing around. I should have changed it to Peapod. But we'll be buying Apple stock, okay. And what we have is this. If I'm receiving these, so there we're buying 2,202, 1131, 730 shares. The question is this system running fine? Seems like it, we're processing trades, but we have absolutely no idea. We have no visibility, like I said, other than some external monitoring tools. So what the channel monitoring pattern is all about is being able to programmatically, oh, that's nice. Oh,
Even
wow.
though you're not buying Peapod stock.
Oh, all right. Wow. No, I'm going to change this over. I bet it's PEA, huh? I don't know what the symbol is. Anyways, but the point is that in our systems, we have no programmatic visibility, and that's what we're going to add. Okay. So when we go back here, now I can kind of stand up here. All right. So there's a couple of things with, those of you who code in ActiveMQ, for example, how would you do this in JMS? It's really tedious. Well, the only way to really do it is to create a queue browser, which gives you a snapshot of all the messages in the queue. And then we can iterate through those messages, counting all of those from the iterator. Ugh, there's a lot of wasted space. In RabbitMQ, what we do is as follows. We connect RabbitMQ. Hold on. There we go. And what we can do is from the channel, which is basically the same thing as a session in JMS, we can actually get the consumer count off of a queue. We can also get the number of messages off the queue. We can also declare a queue, which is the same thing as kind of getting a handle from the queue. And once we do that, we can say get the consumer count, in other words, the number of consumers listening on that event channel, and also the message count. In other words, the number of messages that are pending on there. Now, it's very, very interesting because if you go through something like Stack Overflow, you'll see dozens of postings saying RabbitMQ's broken because guess what? The consumer count works, but the message count will always and forever be 0. So there's 3 things you have to do in order to get this to work in RabbitMQ. And the first is this. So we're now in a consumer right here. We have to connect, and we basically have to set the prefetch count to 1. Because what RabbitMQ does is if, let's say, what's your name? Hugh. Let's say Hugh is the only consumer. Every single message that gets piled into the queue is automatically assigned to Hugh. Therefore, what's the message count of pending messages? 0, because they've all been assigned. They haven't been consumed yet, and that's how it works. So if we set the prefetch count to 1, all those other messages are, quote, unassigned. Okay? Now, I've gone through some benchmarking, and I've done 2,000 to 3,000 messages a second, which is about the fastest I can get on my Mac. And I haven't noticed any performance difference between setting the prefetch count on the QoS quality of service to 1 versus just letting it go. So anyways, the second thing you have to, oh yeah.
Question, so you're using RabbitMQ, you're not using JMS API?
Correct, I'm using RabbitMQ API, exactly, because RabbitMQ implements the AMQP protocol. Right, exactly, so yeah, so this isn't JMS. Now there is a JMS interface to AMQP. Spring has one, for example. But yeah, I'm using the RabbitMQ API, not JMS, exactly, yep. So the next thing is when you do a basic consume, which essentially binds the queue to the consumer, notice that middle flag is false. This is the auto acknowledge. If you don't set that to false, you'll still get 0 every single solitary time, and your systems look like they're running perfect. So then what we do is we do a next delivery. That's the same thing in JMS as a receive in RabbitMQ. And now we have to acknowledge that message because we set auto acknowledge to false. And so that's the trick to getting this to work in RabbitMQ. All right, so let's actually see the result of what we were doing and get some insight into our application. All right, so we go back over to here, and let's see. Okay, so we reset everything here. And what I'm gonna do is start up those consumers. And they are running, and you'll notice we're receiving trades. Now what I'm gonna do here on this side is start up a monitor. And now notice we have 14 pending messages, 13, 12, 11. And so basically, now we have programmatic visibility that we have wait states within our application. In other words, people are waiting. Now, you may have external JMX monitors that can be able to determine this. You may go into ActiveMQ or RabbitMQ console and you can see this, but then how do you take action on that? And so that's why I said this is a very basic pattern, but a foundational one, because the trick is what we need to do is get programmatic information. That's a key to being reactive in any system. Okay, so that's kind of the foundational one. So I am going to, so we have now pending messages 0, and now we have visibility. All right, so like I said, an extremely boring pattern, but one that's necessary because there's a couple of tricks to it to get it to work, first of all. But secondly, this is going to lay foundations onto all the other more interesting patterns now. And that first one that's most interesting is the consumer supervisor pattern. All right. So this particular pattern right here asks the question, how do you untangle speaker cords? There we go. Basically, how can you react to varying changes in load to ensure that the event consumers ensure consistent response time? And notice from a roadmap perspective, the consumer supervisor pattern is both elastic and responsive. And so this is where you get the link between those, because if we have increased load, think about it, obviously our systems are going to slow down. And the key point is, how can we still be elastic? In other words, handle varying load, but maintain consistent or rapid response time. And so that's how these kind of things are linked when we talk about reactive architecture. And so the consumer supervisor pattern kind of looks as follows. It starts with something called a supervisor. The supervisor owns the consumers. Now in something like Scala or Akka, this pattern is very common in these particular languages or frameworks because basically the actors are the event consumers. And the supervisor starts up or owns, I should say, manages those particular actors. Okay, now those event consumers are listening on an event channel. And what happens is the supervisor not only owns those consumers, but is also monitoring that event channel. And what it can do is if the load increases, the supervisor takes programmatic responsibility to start cranking out more event consumers that are needed, and then when the load decreases, to kind of bring those back. And the code is incredibly simple to be able to do this. All right, so let's see the issue. Hold on. All right. This microphone is a pain in the butt. Okay. All right, so, all right. So, we have our trading system here, and we want to be highly reactive. What I'm going to do on the left-hand side here is I'm going to start up the monitor. Notice we have no pending messages, no consumers. And now, I'm going to clear up the top. Now the top part, you can see on here, is going to basically be the receiver. And so now it's just kind of waiting to get trades. And let's process a trade. Okay, so there's 1,245 and 7. This looks perfectly fine until we get a burst of 20 of them. And obviously now we can't react because look at the messages here on the left-hand side. 19, 18, 17, 11, 10, 9, 8, 7. So there's the issue. What we want to do is when we get varying load, these bursts of trades or bursts of orders, what we want to be able to do is react to those very quickly because now these trades are taking 1 second to process. So that means somebody was waiting 20 seconds for that trade. Obviously, we don't want to single thread this. But you might say, well, Mark, why wouldn't you just kind of always have 20 consumers running? Well, because if we don't have any load, I'm taking up valuable resources, CPU, threads, all that kind of stuff. And what if we have a burst of 100? Well, why wouldn't you just start up 100? Well, how about 1,000? As you can kind of see, we need to react to varying load conditions programmatically to be able to optimize the number of threads, CPU, and memory that we have. So let's check out the code to do this. All right. Now, the code, as I mentioned, is extremely simple, but the key is the rules in there. All right, so that's what I kind of want to really focus on. All right, so let's take a look at the supervisor first. The first thing the supervisor is going to do is own its consumers. So I have a list of consumers, obviously. Nothing fancy there. And there's my connection over to RabbitMQ. All right, so the first thing I'm going to do is, actually, if you think about it, the supervisor needs to do 3 things. It needs to be able to start up consumers, needs to be able to shut down those consumers, and it needs to be able to determine when to do that. So there's 3 methods we're going to be looking at here, okay? So the first one here, start consumer. Let's see the start of the consumer. Okay, so I create a new consumer. This is actually processing a trade. Okay, let's say. I add it to my list, and now I spin up a new thread, and notice here, I invoke its startup. All right, and we'll kind of look at the startup and the shutdown because the other thing we don't want to do is when we want to kill a consumer, it may be processing. So we want to kind of, quote, let it drain. So we'll see how to do that as well in this code. But basically, you can kind of see that's fairly trivial code right there in Java to be able to just start. I'm just spinning up consumers. Okay, now let's look at the stop consumer. This one's really difficult. Okay, so the first thing is, this is our first rule. How many consumers do I want out there? So in this particular case, I'm just saying 1. I can create that as kind of a variable or whatever, but the point is that here is where I would have the rule to say, when I stop all these consumers, how many do I want sitting out there? I just want 1. So that's kind of the first rule. So the second technique, I need to get one from the list. And this is just a list. I'm just going to grab the first one. It doesn't really matter. You can create a LIFO queue, a FIFO queue. You can do timings to find out which consumers have been out there a while. I mean, you can make this as sophisticated as you want to, or as simple as you want to in this particular case. Okay, so I said that I'm just going to get the first one, and I'm going to invoke that consumer shutdown method. This is what allows it to, and we'll look at that code, but this is what allows it to kind of shut down gracefully. All right, and then I simply remove it from my list because I no longer am interested in it. All right, and that's the stop. Pretty easy. Okay, now the logic to determine kind of the real supervisor action. So here's the execute. Now what I'm going to do is this. I'm going to connect. So notice that here, I'm going to connect to RabbitMQ because what I want to do is be able to send that channel into each of those consumers. This is incredibly important. We don't want every single one of those consumers making an actual connection to RabbitMQ or ActiveMQ or whatever you happen to be using. Okay, this is the kind of the multiplexing on the session in JMS, and this is the same thing we're doing here with the channel. All right, so I start a consumer because I only want 1. Now keep in mind, this is when the supervisor is starting up. So here's the first rule. How many do I want to spin up first? I'm just going to say 1. Okay, we can put this in a loop to say 10, whatever you want to do. Okay, so now I get the queue depth to find out how many messages are pending in that queue. In other words, how many people are waiting to be processed. Now, here's the first rule. How many consumers to spin up? My rule is going to be take that queue depth and divide by 2. So in other words, if we get a burst of 20 trades, I'm going to start up 10 consumers. And you might say, well, why wouldn't you just make the number of consumers equal to the queue depth? Well, that works fine until you get a burst of 3,000 or 5,000 messages. And we have a limit, so the other thing we want to apply here is something called a threshold. In other words, at some point, this will break. We'll run out of threads or we'll run out of memory. And so when we calculate the number of consumers that are needed, you can do like this time, divided by 2. You can, do all sorts of complicated things. In other words, on the plane on the way in here this afternoon, I was thinking, I should just write the code to show how you can optimize this with a threshold. In other words, if it's less than 20, just spin up 20 consumers. If it goes over 20, then use a doubling up until a certain threshold, like 1,000. And if it goes above 1,000, then just make it 1,000. That would be kind of an example of a more complicated rule. All right, now what I do is I just take the absolute value of the difference between what I have and what I need, and now I can simply apply this. For those differences, if the needed is greater than the size, then just start the consumers. Otherwise, stop them all. All right, and that's it. So like I said, you can make this as complicated or as simple as you want. But again, you need to know what that upper threshold is. So the thing's missing here is, of course, the threshold. All right, and then I'm just going to sleep for 1,000 milliseconds, just 1 second, so this doesn't thrash through. All right, and that is it. So like I said, the code is pretty simple. Now in the consumer, how do I stop gracefully those threads? In other words, those consumers that are actually processing those trades. Well, I have an active switch, and so what I do here is this. On the startup, don't forget, we had startup and shutdown. Basically, I create the channel, I do all the RabbitMQ stuff of creating the queue and consumer, and while it's active, I continue just to wait for the next message. And then, of course, if it's not active, I just simply close. And that's exactly what the shutdown does. The shutdown simply synchronizes on the active and sets it to false. And so that's kind of while it's processing a message, it's going to be in that particular loop. And then it'll simply go out of that loop, and therefore I'm not chopping that message down. All right. Pretty simple code. But check out what it does though. Look at the result. This is really neat. All right. Through that pretty minimal code, let's see what we have here. So what I'm going to do on this side is start up that monitor again. Okay. So now, instead of a consumer that I had on the top here, what I'm going to do is start up a supervisor. Now look what happens on the right-hand side. Number of consumers is now 1. Why? Because I had said in my rules, start up 1 consumer. Okay, so let's watch what happens on the bottom window here when I send something. Okay, so message received, no pending messages, everything's running fine. Suddenly we get a burst of 20 trades. So what I'm going to do is bring that to the top and ready, go. And now notice all of a sudden consumers 9, 6, 2, 1. We had 11 messages, 5, 3, 2, 1. So instead of 20 seconds, it only took 1, 2, 3, 4, 5 seconds to process that burst. And notice what it did over here on the upper left-hand side. You can kind of see, oh, we just had a burst. Started all these consumers. It calculated it based on the fact of that doubling kind of thing. And as a matter of fact, we can kind of see the doubling. There was 20, it went to 9, messages 11, went to 6, 5 goes to 2, so on and so forth. All right, so let's start that monitor back up, because now we get another trade, no big deal. Now we get a burst of 100 trades. Now watch on the left-hand side of the screen there. All of a sudden we get a burst, messages 99, 50, 25, 13, 7, 4, boom. So we had 49 consumers at one point going down. You can see as you vary those rules, it's going to affect the responsiveness. But basically, what if, should we try 500 trades? Immediate burst of 500 trades. Oh dear. Boom. Yes. And it works. So you can kind of see, now 500 trades, 1, 2, 3, 4, 5, 6, 7, 8, 9 seconds. And so that's what I mean about being reactive. Now notice how many consumers I'm back down to, 1. So this is managing that elasticity, okay? Now, after the really cool producer control flow, we're gonna see the thread delegate pattern, which is very similar to this. But the cool thing, to give you a little kind of heads up about some really cool stuff in the thread delegate, is that is able to spin up all these various threads to do all this stuff concurrently and preserve message order. Because that's one of the gotchas on this pattern, isn't it? That while we're supplying this great elasticity, message order is completely going out the window. Right? And so hang on until we look at the thread delegate, because I'll show you how to actually preserve the message order while running things completely in parallel. All right, now, if I were to, but in the interest of time I won't, if I were to, no, you know what, let's do it. No, it takes too much time to restart. If I do a burst of 5,000 trades, what do you suppose would happen? Think it would work? Of course not. No, I'm going to get an out-of-memory condition because I haven't set any sort of threshold. And that points to, and as a matter of fact, that's what I want to kind of back up once. Hold on here. I want to back up just a little bit because I want to show you this pattern right here. Let's go here and back one. Yeah, okay, good. So basically, so let's say, I won't demonstrate it because then I had to restart and I had to change all my code to get the new IP address and all that kind of crap. But if I were to go 1,000, it'll work. If I go to 5,000, it immediately fails. And all of a sudden you say to yourself, oh, so this really is limited, right? In other words, to whatever my threshold is, my max. No, completely false. Because here's the key. You see these combinations of supervisor event consumers? I have that grouping in multiple virtual machines. And so I scale this out horizontally. So in other words, virtual machine A, Hugh over here, has a supervisor with up to 1,000 event consumers. And what's your name?
Anne.
Anne? And then Anne is another virtual machine or another container that has a supervisor with all these 1,000, and then so on and so forth all the way across the room. And so we can continue to scale this out in these groupings, and that's kind of key. Now this is one place, by the way, where kind of the actor model does fall apart. Because whether you're playing in Akka or Scala, the point is those actors and supervisors are combined into a single virtual machine. Now, I can access a remote mailbox easily, no, not easily enough. I can access a remote mailbox in Akka, for example, with about 2 to 3 pages of configuration code. However, I cannot access a remote supervisor. And so when we look at the thread delegate, I'm going to show you kind of a way to be able to combine those kind of patterns or those languages together, frameworks I should say, together, to create a really powerful, powerful solution. All right, let us now look at another really cool pattern called the producer control flow pattern. So this says this: how can you slow down message producers when the messaging system becomes overwhelmed? In other words, it's about to crash. And this is being reactive. How can you programmatically tell all of you? So everybody here in this room is basically going to be sending trades. You're going to be systems that are pushing out trades. And basically what I want to tell you is slow down. And this all has to do with being resilient. Now, it's kind of interesting. Here's the pattern itself. You have an event producer and event consumer. And of course, we send events to the channel and they get consumed. But the problem is we keep getting more and more events. In other words, even though we ramp up our event consumers as much as we can, we still cannot keep up with the number of messages. So basically what I want to do is tell this event producer to slow down. And they say, oh, okay. And as long as they slow down, then the systems become almost self-healing without any external person knowing what's going on. And this is all happening programmatically, and that's one of the keys. All right, now it's interesting that you might think, especially if you do currently code in ActiveMQ or RabbitMQ, you say, well, wait a minute. Both of these, this is also known as applying back pressure. Well, it's not known. It's similar to the concept of applying back pressure. But basically, the interesting thing is RabbitMQ and ActiveMQ both have producer control flow. As a matter of fact, if you look at the ActiveMQ.xml on the broker element, it will say broker equals blah, 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 producer control flow equals true, threshold equals 1,000. So why do we need to worry about this pattern at all? Why? Because it's a shutdown versus a slowdown. In other words, the producer control flow built into RabbitMQ and ActiveMQ and HornetQ and StormMQ and all these other messaging brokers basically will stop all of you. So if you were to try to execute a send, for example, or a basic publish, what would happen is you would get an exception. So it kind of shuts down. This is kind of one of the cases where if you do enable producer control flow and have it set too low, you get a burst of orders, burst of trades or whatever, and all of a sudden the system comes down. Or so it seems to all the consumers, or I should say the producers. And so that's the difference. So what we want to do is have that kind of be a very last resort. But programmatically, I want to tell all of you to slow down. So let me show you the issue here. All right. Okay, so let's see the issue. Let me put my old man glasses on again. All right, so let's see. Let's stop that. We'll stop everything here. And stop that one and clear that. Okay. So what I want to do, let's start a monitor here. So we're going to be monitoring to see what's going on, so we have some visibility programmatically. And I'm going to start just a continuous consumer. And so this is just kind of going to wait on trades. Now watch what happens here. Notice the consumer count went up to 1 on the right-hand side. Now we're going to produce a whole lot of trades. So let's see, continuous producer, with no control flow whatsoever, and ready, set, go. Now, what I want you to do when I hit go here is watch the pending messages, okay, and kind of keep track. So now, notice for 987, 23, and notice here, 2, 3, 4 messages pending. So now we're starting to get a wait state. And so here, I could apply the consumer supervisor to try to handle that load. And let's say I do apply that consumer supervisor, assuming message order is okay. The problem is, as you can see, pending messages is going to continue to increase forever and ever, and this will blow up. So what I want to do is tell this producer on the bottom to slow down. Okay, so what I'm going to do is I'm going to stop him now, though, so that we don't end up really blowing up. And now we're going back down. So while that's draining, let me show you the code. So here's the issue. Look at this. I much prefer standing than sitting. All right. Cool. All right. So here's what we're looking at here. We need to add another component called a flow monitor. What this is going to do is it's going to be monitoring that event channel. And basically, when it hits a certain threshold, it's essentially going to be monitoring. And by the way, we can monitor anything here. I'm just going to do the number of messages, kind of the most simplest kind of metric. But I can also do threads, CPU, I can check any sort of level of system health programmatically. And basically what I want to do is once I reach a certain queue depth, I want to basically tell all producers through something like a fan-out exchange or a topic exchange or something like a topic to basically slow down. Okay, and so what's going to happen is that event producer is going to slow down until the system's repaired. Then I'm going to tell it to speed back up. Okay, and so that's kind of the example. So let's take a look at this flow monitor first, okay, because this is kind of where most of the code sits. All right, so let's take a look at the execute method here. First of all, we do a connect. All right, now, first rule. When do I want to enable producer control flow? In other words, when do I want to tell every single solitary one of you, slow down? And I'm going to say, when that queue depth gets to 10. Now, obviously I'm doing it low because I don't want to sit here all night. But once that reaches 10, That's the threshold that I've built into this to say, all of you need to slow down. Now, I've got a control flow flag here because what I'm going to do is this. I'm going to get the message count. In other words, what's the current queue depth? Now, if I'm not in control flow and the queue depth is greater than my threshold, then basically what I want to do is enable control flow. We'll look at that code. Okay, so I want to enable that control flow. Otherwise, if I'm in control flow, in other words, I've told all of you to slow down, and the queue depth is less than or equal to, second rule, the threshold divided by 2. That's my rule. Then, and I want to get back to that piece, then I'm going to disable the control flow. Now, this is a practice that most thermostats use. It's called hysteresis. Try to say that 3 times fast. Hysteresis. And basically, what we don't want to do, notice that rule there, if we're in control flow, in other words, I've told all of you to slow down, when do you speed back up? Well, if the threshold is 10 and it goes to 9, oh, go ahead and speed up. Then it's immediately going to go to 10, and I'm going to get this ping-ponging. And that kind of ping-ponging, for example, will burn out a thermostat. So thermostats have this kind of built in as well. These are how these work. In other words, when it reaches a certain point of health, then speed up again. Because I know it's probably going to reach that at some point again. And so this kind of points to that reactive part of responsiveness. Remember, timely, rapid, and consistent, exactly. And that's why this rule is so important. Because the last thing, you get those systems where it's like, now it's slow. Oh, now it's fast. Oh, now it's slow. If you want to drive your user community crazy, then just, if it's not less than threshold, greater than threshold, less than threshold, greater than threshold, and it's not consistent. However, you get those times when all of a sudden the users are like, oh, I'm sorry, the system's a little slow, because it's repairing itself. That's reactive, because now we're acting in a consistent and timely, but more important, a consistent manner. So that system is slow up until a certain point, and then it's going to speed up. And once we reach a threshold again, it's then going to slow down. And so that's what we're doing with these 2 rules right here. Okay. All right, so I'm just going to do threshold divided by 2, and I'm going to check this every 3 seconds. All right. Let's see. The other thing we need to do, enable and disable control flow. All right, now what I'm going to do is I'm going to send a message to all of you. All of you in this room are producers. You're producing all these trades. I'm going to send you a message to slow down. And all I'm going to do, and you're all listening, all I'm going to do is simply send you a flag. And so what I'm doing here is I'm just basically taking a Boolean. Now everything in RabbitMQ is a bytes message, basically. So all I'm doing is I'm converting it to bytes and sending it along. And then returning that value to me so I know whether I'm in control flow or not. Excuse me. And then, of course, I do the same thing with disabling. I simply set it to false. Now, this is where you can get, this is going to be interesting because I wish I could show 2 pieces of code at the same time. Because all of you, and we're going to look at this code in a second, are all going to have a delay. Okay, so I'm going to tell all of you to sleep for 3 seconds before sending another trade to me. And that's a slowdown. Okay. Now, whose responsibility should it be for determining how long you should slow down? And that's where the design comes in. You can bake that into this message. In other words, I can send all of you, and this might make more sense, to say, instead of all of you having a hard-coded or a configurable value of 3 seconds, I can send it and say, looks like we're in trouble. All right, everybody slow down for a second. Is the system repairing itself? Yep. Then we're good. I've just saved some time. But I send you guys all something that says, slow down for a second. Is the system repairing itself? Don't forget, I'm the flow monitor. Nope. All right, do 2. How is it now? Nope. Okay, now do 3. And so I can kind of incrementally do that. And so this is where you may want to send that information to the producers of how long they should slow down. Okay, and actually let's take a look at that producer. So the producers need to start a listener. In other words, they're producing all these trades, but at the same time, they need to listen for these slowdown events. And so basically what I'm going to do here is I do all the RabbitMQ setup, blah, 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 blah. And now I simply listen for messages. And that's what the next delivery. It's the same thing as JMS receive. And here I set my control flow equal to the body of that message. So basically I'm extracting that Boolean, setting a control flow. Now, here's that delay flag. If I'm in control flow, then set the delay to 3 seconds. Otherwise, if I'm not in control flow, set it to 0. And this comes into play right here. So notice when I'm producing all those messages, in other words, when I'm producing those trades or those orders, I set the trade to the queue and then I sleep for that delay. If I'm not in control flow, I sleep for 0, which means don't sleep. And that's what I mean, this is the information I can pass to all of you. So that's kind of the 2 different modes or ways you can actually do this. All right, now this is cool because sometimes if I'm bored at work, let me put this here. Sometimes if I'm bored at work, I actually spin up this example and I kind of watch it. It's like those virtual fish tanks, you know, you kind of veg out and watch the fish floating. My virtual fish tank is this example. So this is really cool. All right, so I've got my consumer here. It's now waiting on trades. Notice we still have our monitor running. Consumer's 1. Now, in this particular case, I've got a producer that does have control flow. Now I need one other thing here, don't I? I do. Okay, I need a control flow going. So let's move this up, and let's put a control flow right here. The control flow is, flow monitor. Okay, so now what that flow monitor is doing, it's doing the exact same thing that the top monitor is doing, only it's got all that logic to do the thresholds. Okay, now let's process some trades. Now what I want you to do is this. As they're processing, notice I'm receiving trades much slower than I'm processing them. Notice the pending messages here on the right-hand side, 4, 5. Now what I want you to do is when that gets close to 10, I want you to watch the flow monitor here and then watch the producer. 8, 9, now watch what happens with the flow monitor. 10, 11, there it goes. Enable producer control flow. Notice the producer, notification to slow down. And so it slowed down to 3 seconds between each trade. Now notice what happened here. It went to 11:10, went back up to 11. That's to avoid that ping pong. In other words, don't forget, I did not shut down those producers at all. Now, it's going down to 7, 8. So notice, unlike the automatic shutdown piece that you get with the brokers, I'm still producing trades. Now watch what happens here, disabling the system back to normal. Look at how fast that bottom left-hand one is now flying. And of course, we're going back up to 8. Now the system's responsive, and now enable producer control flow. There it goes, enabling it, and now it slows down all those guys. And this system will run forever. In other words, this is going to keep going up and down and up and down. So you can kind of see it's a very powerful pattern. But who can tell me who can tell me a couple of really bad things about this? I mean, it looks really cool because this is highly reactive.
I have a question. Maybe it's an implementation detail.
Sure.
Why do you need a separate channel to asynchronously control those producers? Why don't you just delay the acknowledge of the producer? When you post messages to the queue,
Right.
when the queue depth is higher than the threshold, slow down the acknowledgement of the producer.
Well, so you're talking about in the producer to be able just to...
Yeah, because it doesn't receive any acknowledgement, it won't.
Well, keep in mind here on the producer though, we probably don't have any sort of auto-acknowledge. In other words, when I'm creating a trade, I'm just sending it out. So in other words, there's no mechanism, I guess I should say, to know. So the only thing we can actually do in that case is for every single one of you to say, what is the queue depth? Should I slow down? But you have no idea how many consumers there are. In other words, it's not the responsibility of the producer to know to slow down or not.
So when I post a message, until I receive the acknowledge from the queuing system, I'm gonna be blocked.
Oh, you'll receive it immediately, I understand. So when I post a message, I receive that acknowledgement back immediately because all I'm doing, keep in mind, is I'm sending it to a queue or I'm sending it to an exchange. It's still accepting it, it's just not being processed yet. You see, that's the problem. From my perspective, I'm sending it out. Now, are you talking about like a request reply kind of thing where I'm actually waiting for the reply and timing that?
Right, for example, in GenMats, right?
Yeah.
When you're a producer,
Sure.
until you turn on the acknowledgement mode to be
Right.
reliable,
Okay.
until you're done with it, your posting is not finished. You'll be blocked.
That is true. However, what we're talking about is it's funny I use the word a reactive versus a proactive way. Not to be confused with reactive architecture. But the problem with that is if I time out, in other words, let's say I need a confirmation number from posting that trade. So I send a message to a queue. I get an immediate acknowledgement back that that was posted, but then I'm listening on another queue for that confirmation number. And I'm waiting and waiting and waiting. And let's say I wait 10 seconds. In that case, I need to probably time out and then back that out. So in that case, now it's my responsibility as a producer to manage all that stuff. And so yeah, that would be one way of doing it, but I'm setting the responsibility all on every single producer. And we have a whole bunch of producers in this room. There's some of them in the corner over there. So it's really a matter of responsibility. But there's a couple of issues with this pattern. I mean, it's very powerful. Can you think of definitely one issue?
Well, I think I'm used to telling producers to slow down, but I guess there could be situations which you just have to accept everything done.
You have which?
You have to accept every message that you can't tell them.
Oh, right, yeah. So I'm going to turn that around and say, yeah, what if the producer just decides not to slow down? I mean, I'm trusting that all of you are going to code this, and all of you are going to slow down to the right timing. Yeah, so you're, exactly. So, and this is where we can get very sophisticated with the producer control flow, because the folks here in the back area are really important trades. So you're not going to slow down at all, but we're all going to slow down. So you can actually divide this into classes of clients that I'm going to send the messages to. Right? But therein lies kind of a key point. It's a highly intrusive pattern. In other words, every single one of you has to code this. And what if I've got advisors all over the country? I don't have access to those systems. I mean, I can't send somebody a chunk of code and say, here, add this to your producers. And so I may not even have access to that. So while it's a very powerful pattern, as you can see here, this will just keep ping-ponging forever. It's a highly intrusive pattern. So how can we do this same thing without being intrusive? And that, let's kill this guy. Hold on, let me see. Let me stop this one. And stop this guy. And we've got 6 messages left. We'll continue to let that drain. Which brings us kind of towards the second to last pattern, which is probably the most powerful one. That's the thread delegate pattern. And the thread delegate is one of my favorites. I've implemented this several times in a variety of kind of complexities. But basically, how can you consume messages faster than they're being produced? And basically, this points to 2 things, resiliency and responsiveness. All right, so the thread delegate pattern kind of looks as follows. With event producer, which sends messages to a queue. Now keep in mind, the problem statement is, we've got way too many messages coming in. There's no way, even if I use the consumer supervisor, there's no way I can handle the incoming load. So how can I consume them faster than they're being produced? So what we have as a consumer is something called an event dispatcher. And what this does is it delegates the work over to a thread, hence the name thread delegate pattern. And that thread delegate does all the work. Now, optionally, if it does need to communicate some information back to the event producer, then that thread delegate's responsibility is to do that. And notice the thread delegate up at the very, very top kind of top left of that, I put a little queue there. So each of these threads could also have, and usually does, have its own queue as well. Now this could be a regular like JMS or AMQP queue. It could be a java.util.queue, and it depends on the implementation, but basically you can queue these up as well. And so think about this. We cannot consume messages faster than being produced. And when that happens, what's going to happen? The queues are going to fill up. We're going to run out of memory everywhere. We're going to run out of threads, and everything will come to a crashing halt. So what I'm doing is basically pulling those messages off as fast as you can. So watch this. The event producer produces a message. It goes to the dispatcher. All the dispatcher does is say, here you go, and it dequeues it and hands it off. Because the problem with the consumer supervisor pattern is this. I've got 100 consumers, but guess what they're doing? They're processing a trade. So while they're processing that trade, they cannot dequeue any other message. And so what this consumer is doing is simply dequeuing and sending it off to other threads that potentially have their own queues as well, okay? And so the thread delegate gets the information, and let's say it needs to send back a confirmation ID. In that case, the thread delegate's responsibility is then to send it to a queue, which then goes to the event producer. Now, let's see the issue, and then I'm going to show you actually how to run this in parallel and preserve message order. Okay. All right. Cool. So here's the issue. So let's clear this. Okay, I'm going to bring this guy down here. Now, let's see. Good. So we have 0, 0. Okay, so we're all cleared out. So what I'm going to do here, I'm going to start a thread consumer. Oops. Okay, so that's a consumer. This is listening on trades. Now, what I want you to keep an eye on is the monitor. So watch this. Ready, set, go. Look at that. There, we're placing one trade. So we're already up to 7 waiting messages. So clearly I can spin up other consumers, but the problem here is I'm never going to keep up with this message flow here. And so therein lies the problem. As a matter of fact, I better stop this now before it really does kind of crash things. So did you see how fast the messages were being produced? Okay. So while that's draining, I want to show you a couple of interesting things about this. So what you might see is the fact that in that example, well, why couldn't you just use the consumer supervisor pattern and just start spinning up more consumers? And there's a couple of differences between the thread delegate and the consumer supervisor. This pattern we're looking at now is all about scalability. In other words, I don't have varying load. I just can't keep up with the demand. I've got 2,000 messages a second coming in, and it's not about variable scalability. But the consumer supervisor, keep in mind, is always monitoring. It's always about spinning up and slowing down, spinning up and slowing down. But I've got a consistent high load that I can't manage. And so that's one of the differences, is that this is more about scalability, consistent consumers. You know, the other difference is about the consistent consumers, but the consumer supervisor is about variable consumers, spinning up, tearing down, spinning up, tearing down, okay? But the other difference here is that we have decoupled event processors. In other words, keep in mind, I've got one and only one consumer, and that's the delegate. And what it's doing is it's handing it off to all of you guys. And so these are decoupled event processors, whereas with the consumer supervisor, I'm going to spin up a process that's listening on a queue, which is going to receive messages. And so that's the other difference. But now we get to 2 of the most important differences. Because with the thread delegate, I get near linear performance, which with the consumer supervisor, I get diminishing performance. And let me show you an example of that. If you look at this chart right here, I've got 500 messages that need to be processed right away. In other words, I just got an immediate bulk of 500 trades instantly. And each of those take 100 milliseconds. So if I spun up 500 consumers, presumably how long would it take to process those 500 messages? 100 milliseconds, right? But look at this chart. What happens is it actually takes 400, close to 400 milliseconds when I spin up to 500. So with competing consumers, what you call like spinning up multiple consumers, you can see it's sort of linear until it gets around 200 or so. Now this is my own benchmark, but it gets around 200, and then it starts going up and up and up. Now there's a lot of the kind of the law of diminishing returns happening here, but really what's happening is it's the broker itself that has to manage all those consumers. I mean, when I get a message, I have to say, who's available? Who do I need to give it to? So let's say we only have you two, Ann and Hugh here, and I get a message. Which one of you is available? Oh, that's a quick answer. Hugh goes, yeah, me. I can assign it, but all of a sudden we get 500 people in this room. And it's like, who's available? Well, that just took a while to figure out who's available. And so that's why we get this law of diminishing returns. But look what happens with the exact same benchmark with the thread delegate pattern. Watch this. All of a sudden, as I go to 500, it's almost linear. If I have 1,000, it'll be 1,000. Why? Because I only have one consumer. That's why. So that's one of the big differences, is I can get that kind of linear performance. But probably the biggest difference is this, that the thread delegate can actually keep up with that number of messages in parallel and preserve message order, whereas you cannot possibly do that with the message order, with the consumer supervisor. So the interesting thing is, you might say, that's impossible. How can you run 500 messages in parallel and guarantee message order? And so in the NFJS tour, Michael Carducci is one of the speakers. He also happens to be a magician. And he does a talk called The Art of the Impossible, which is just an awesome talk, because he'll do a magic trick and he'll say, can I turn this handkerchief into an egg? And he would say, no, that's impossible. And he goes like this and does it. And it's all sleight of hand, of course. And so I like to take that kind of theme and say, no, it's not possible. It's not impossible. Here's the premise. The premise is this, and this holds true 99% of the time, that not every single message in your system has to be ordered, but the context of those messages need to be ordered. In other words, messages with any particular context must be ordered. So let me show you an example. In trading, we have things called cancel rebooks. They're called corrective trades as well. So here's the thing. I do a place for Apple, for that brokerage account, for 2 million shares. And that gets placed. Okay. So the problem is, at the time, at the price, and when we're talking about 2 million shares, I had enough money in that brokerage account A-136. But by the time it was about to be executed, the price went up, and I do not have enough money. So immediately, almost instantly, there's a cancel of those 2 million and a rebook for 1.8 million. Now I have enough money because of the price difference. Okay, those have to be in order. If they're not, disaster will strike. Okay, so yes, trades have to be in order. However, only within a context. Because look at this example. Here we have a place for Apple, a place for Google, a cancel for Google, a cancel for Apple, a rebook for Apple, a rebook for Google. These are all intertwined. Now, these trades, numbers 1, 4, and 5, absolutely have to be in order. And furthermore, these Google trades right here, 2, 3, and 6, absolutely have to be in order. But those groups can be run in parallel. And that's exactly the premise of guaranteeing message order. It's whatever that context is. Maybe it's a customer, maybe it's a shipment ID, an order ID. In this case, it's a combination of the brokerage account with the trade. So anyways, that's the secret sauce. So here's what you would do. The event producer sends a message, goes to the event delegate. The event delegate has something called an allocation map. Now, this is a map if you have to preserve message order. This is a map that says which one of you is processing which context. I'm just going to use simple. Okay. So I know that Ann here is processing Apple currently. So if I get another Apple trade, basically I know to send it over to that particular thread or consumer, or I should say processor. However, I get another in for Google. Who's processing Google? No one. Okay, I'll start a new thread then and add that to the allocation map. And I do some sort of timings to say if it's been like 3 minutes without a trade, then just cancel it out because then Ann's available to process any other kind of symbol. And so what it does is it basically groups that context within certain threads. Okay, now this can also get really, really complicated because you may say, well, you're still single threading everything through. That's right, so now I can do groupings, but that's going to require striping at the producer. So what I can do is this. Check this out. I can stripe symbols A through M going up. So in other words, Apple and Google are at the top end here, but now N through Z go through a separate event delegate in a separate virtual machine or container or whatever that's doing, for example, pharmaceutical spiders or technology spider stock. And so you can kind of see I can use any sort of striping. As a matter of fact, if I stripe on the first letter, I can do 26 of these groupings in parallel. And this is how I get 2,000 to 3,000 trades a second with message order. It doesn't have to be trades, it could be any context. I just happen to be using this in one of my domains is trading, so it's a great place to show where message order is required. Okay, so let's look at some code and see how this thing works, because this is really cool. Then we're going to try to stress the system out. Okay, so in the dispatcher, all the dispatcher's responsibility for is as follows. It is the consumer. So it does a basic consume, which binds itself to a particular queue. And now, all I do is I simply get the next message and I delegate it. And so I'm just going to start a new Pojo thread processor and just simply start the thread. Now, what you can do here, this is the simplest code possible. So in other words, it's going to start a thread, stop a thread, start a thread, stop a thread, so on and so forth. When it's not needed, the thread will just die. I could have an allocation map to say, hey, when I spin up a thread, are there threads available if I don't need any? In other words, kind of combine that producer-consumer flow. So this is where I would also add that allocation map if the message order was actually required. All right. So now, last demo, let's check this out. Okay. This one's really cool. I'm going to try to stress this one out. But you're going to see a lot different, a much different story this time than the other. All right, so this particular case, we'll keep our monitor up just because it's kind of interesting. Actually, we'll need that because you'll be able to see what's going on. Let's see, kill that. All right, so what do we need here? So for the thread delegate, I'm going to need a delegate and a dispatcher. So let's put the dispatcher up here. All right, whoops. Thread dispatcher. Okay, so where the consumer is, I'm going to start that dispatcher, and now that's waiting on trades. Okay, so don't forget, the dispatcher is the only consumer. Notice the consumers in my monitor shows 1. I only have 1 consumer here. All right, and we're going to need a couple of other windows here, because we're going to actually play around with a lot of stuff here. Okay, so let's start sending those trades really, really fast. All right. And thread producer, okay, are you ready? Set, go. So notice, all of a sudden it's cranking out threads and now it's producing them. And it is actually keeping up. The cool thing is, look at this pending messages. 0. It will always, forever be 0. So that's kind of one of the interesting things. So keep in mind what this pattern is doing, it's dequeuing as fast as possible and delegating it. It's like spraying it out to all these threads. And unlike the consumer supervisor, yeah, but what if you run out of threads? Okay, no problem, because each of those threads will have a queue. And that could be an internal queue, like a Java util queue, or it could be another instance of RabbitMQ or ActiveMQ that each of those are listening on. And so it's basically dispersing it out and processing it in parallel. As a matter of fact, let's double my throughput. So I'm producing a trade about every 10th of a second here. Let's double that. All right, thread producer, you ready? Set, go. Now, I just doubled my load. And notice, now to maintain that consistent load, it needs 8 threads. No more, no less. And 0 messages pending, everything is taking a second to process. So you can kind of see the differences between this. As a matter of fact, now what we can do, I like playing around with this, let's start up another consumer or another dispatcher. Because don't forget, we have these dispatcher thread combinations. So let's start up a new thread dispatcher. Now watch what happens to the upper left-hand window now. So this starts up, and now all of a sudden both of them are just simply balanced out. It's not, each of them are consuming 4. If I start sending this, let's kill this guy, and now notice each of them go down to 2. If I kill this guy, now single dispatcher goes back up to 4. Now you want to see a difference here. Watch this. If I were to do this same thing, you might say, well, there we go. Okay, so now the system stops. So basically, keep in mind, that is a consistent load. Now what happens, and let's see if I can remember how to do this, if I started up a supervisor. Okay, 1 consumer, 0 pending messages. Now, watch the difference here. Now I'm going to crank all those trades out again. Message received. Look at what's happening with the pending messages. Same throughput. Messages 3, 2. Now I've only got 2 consumers because keep in mind, the consumer supervisor pattern is about variable load. So I've got rules in there to determine how many consumers I want. Remember what my rule was? Queue depth divided by 2. But the thread delegate is all about consistent throughput. These are 2 entirely different patterns. So this is not very reactive, because what this is doing is it's trying to say, oh, I've got additional load. What I really need is 4 consumers to manage that load. So I've always got queue depth. As a matter of fact, now it's up to 3. So let me kill this guy. Let that go back down. And everything is done. See?
You
and then
you didn't use flow control with that, right?
Correct. That is correct. Yep. And well, that's correct. Yeah. Yep. Because it was only 2 to 3, 2 and 3. But I've always got wait states. Is my point. Because keep in mind, and now I'm going to start up the dispatcher and run this again. And now notice the message count is always 0. Because this is about scalability. This is about maintaining a load, a consistent load. So you can kind of see these different patterns. And like I said, through kind of those games of those allocation maps with the thread owning a certain context, clearly now what I can do is preserve message order as well. So this is such a cool pattern. All right.
Excuse me.
Yeah.
I got a question. So I may be wrong, but aren't these messages queued up inside the threads that have been spun up by this thread controller thing?
No, in this case they're not, because what I've got is consistently 4 threads that are being processed, right? So there's no queuing that's needed with those 4 because it's able to maintain that load, that constant load. So there's no queuing. Now, the place where the queuing would occur is if I cranked this to where I was producing, let's say, 2,000 messages a second, but in my virtual machine, my JVM, I can only maintain 1,000 threads. And so in that particular case, I'm not going to be able to keep up, which means that I can now queue those particular threads with further things to get rid of that backlog.
Okay. So in your thread delegate pattern, there is no limit on the number of threads that can be spun up?
Oh, there is. Oh, there's absolutely a practical limit. Yes. So if I go back here, so what he asked was, well, with the thread delegate, isn't there a practical limit? And the answer is absolutely, but I want to show you that guy again. Yes, so what we can do here, now let's assume that order is not important for a moment. Okay, in that particular case, if you look at the screen that we have here, those event delegate threads can each be groupings in their own virtual machine, right? In their own JVM, in their own container, whatever. So I can have 5, 6, 7 of those running. And so in that particular case, the difference here though, and keep in mind the difference, because you could say, well, can't you do that with the consumer supervisor? No, because the consumer supervisors, those consumers are receiving messages. They receive a message, process a message. Give me the next message, process it. Those messages will be backlogged. They will start stacking up. This is draining those queues out as fast as possible. The other difference is those threads have queues with them, whereas the consumer supervisor, those consumers are already listening to a queue. It can't be listening to 2 queues at a time. And so those are the inherent differences between these two patterns. Yep. So what I want to do to kind of close is show this. Boom, boom, boom. Yeah, so I'm not going to demo this, but I want to show this one because when I show the combination of them, this is a very important pattern in reactive architecture. Because when we talk about reactive
Yeah, in all the examples that you have shown so far, you are using just a single broker. What happens if this broker goes down? This question might be out of the scope, but what happens if this broker, for whatever reason, or this JVM just crashed?
Right. So the question is, in all this I've been showing a single broker and stuff, and what if that broker becomes a single point of failure or crashes? Generally, you would not, in most reactive production environments, have a single broker. In other words, for example, with RabbitMQ, I can have a cluster of nodes, and then I can have a cluster of node clusters. And so I can cluster this across many different physical machines. So generally, even with ActiveMQ, you can do the master-slave kind of arrangement to protect that kind of single point of failure. Yeah, and there's failover protocols in both RabbitMQ and ActiveMQ to manage that. But good observation though, because when we're talking about reactive architecture, what we're really looking for is what are the hotspots and how can I monitor those and programmatically react to those? And as we've seen, we've been able to do that so far with just 3 of these patterns that we've looked at. Okay. All right, so the last pattern that I'm not going to demonstrate, but I want to show because it is critical, is the workflow event pattern. So one of the things that happens in most reactive architecture is the fact that we are using asynchronous communication. And anytime you're doing asynchronous communication, or even synchronous for that matter, what happens if a message gets lost? What happens if it gets stuck? And that's where the event workflow pattern comes in. So in other words, how can you handle error conditions without failing the transaction? And so in other words, this is where we start to get to more reactive programming style, where we're concerned now about an individual request, not necessarily a system coming down with that we're dependent on. So I have been using the workflow event pattern for probably about 20 years. And I've implemented this about a dozen times. And so this pattern is not new, but it is a reactive pattern. So here's what happens. Keep in mind, actually I want to back up once because, there we go. Do you remember resiliency? What do we do when error occurs? And it's how the system reacts to errors through containment, isolation, or delegation. And what we're going to look at is the delegation aspect in this case. Okay, so we have an event producer and event consumer, and what happens is this. We delegate the error handling to what's called a workflow consumer or a workflow processor. Okay, I'm going to show you the 2 different ways. So the first method, now, oh, by the way, anytime we're doing asynchronous processing, what happens when we get an error? What do we usually do? Write it to the log. Right? And we all look at those production logs, right? It becomes complicated because there's no one to talk to say, hey, there's an error happening. So there's two common ways, there's multiple ways, but two common ways I want to show you on this pattern. The first is that the workflow processor says, ew, this is an ugly error. I have no idea what to do with this. So what it does is it sends it off to some sort of dashboard, like a workflow dashboard. And I've created, like I said, dozens of these in various forms. Most of the time they look like Outlook, for example. So a message comes in. So a trading supervisor or a warehouse manager or something like that, blah, blah, blah. They'll always have this in the background. All of a sudden, ding, another message comes in that failed. And so here's what happens. You've got a dashboard that is able to, a person is able to manually fix the error and then resubmit that transaction. So here's what happens. Let's say an event consumer is processing a message and gets an error. In the spirit of reactive architecture, it is not the responsibility of that event consumer to worry about all the possibilities of how to fix that error. It's about delegation. So it delegates that over to a queue that the workflow processor is listening on. It picks it up and it says, oh, I can't do this. This requires manual intervention. And it sends it over to the workflow dashboard. Somebody looks at the message and says, oh yeah, that darn middle name is missing. Yeah, we get some, middle names required and we have a supplier that never sends us a middle name and yeah, this is annoying, so they just put X or something like that. And then they resubmit the transaction, which then goes back in as if nothing went wrong. There's even a better way to be reactive. There are times, and almost all systems have this, where there are these common errors that occur and you cannot fix them upstream. So for example, we get trades coming in from an advisor and they're hand typed. This still happens. And a couple of users continually type 500 shares, and they type the word shares. And what we do is we extract that string into trade directives. And the problem is when we try to convert that to a long, we get an exception. And so it's a known fact. The word shares is sometimes there. So what we can do, we get that error, we send it over to the queue. The only responsibility of that delegation, the only responsibility of the consumer is to send it to the queue. Workflow processor says, oh yeah, the old shares problem. And they parse out the string, they take out shares, and then they resubmit it with no human intervention. And that's what this pattern is all about. All right, so, oh yeah.
Is that the same thing as a dead letter queue?
Not necessarily. So is this the same thing as a dead letter queue? The DLQ really is where, like on timeout conditions or expiry conditions, and so if you say, after 10 seconds expire this message, usually it just doesn't poof, disappear. It goes into something called a dead letter queue. Or if I send something to Amy, right? No, Ann. Ann, right? Oh, okay. I can't remember if it's Amy or Ann. Hugh, I remember your name. If I send something to Hugh and he throws an exception, it comes back to me. I'll do that 7 or 10 times. And as a broker, it's like, well, this is called a poison message. I'm not going to do that, so I send it to the DLQ. But the problem is a dead letter queue, you can kind of simulate that to where this queue that you see in between the event consumer could be a dead letter queue that an event processor is then picking up. But the problem is with the DLQ is unless you configure this pretty sophisticated, all messages from everybody come into the same queue. And with this pattern, generally this is a known consumer. And so that would be some of the differences between that and a DLQ. Yep. All right, so the very last thing I want to show you is combining these, and this is where it gets really cool. So this is how we should be architecting systems. Check this out. So we start with that really cool event dispatcher. This is a great way of managing high consistent load, okay? However, there are times when we have varying load. So what we do is we add the consumer supervisor on top of that event dispatcher so that that supervisor owns those dispatchers. And those dispatchers in turn owns the threads. Now, we add the workflow processor, workflow processor, we add that workflow event pattern we just saw in there to handle any sort of error delegation that occurs. And we also add a flow monitor here for that producer control flow as kind of a last resort. And if we look at combining all of these, what we find is this. We've got responsiveness. So if we look at all the quadrants of reactive architecture, we've got responsiveness right here with this event dispatcher. We've got elasticity with the consumer supervisor. With these two right here, we've got resiliency with those two patterns. And of course, all this system that you're seeing right here is linked, which of course is message driven as well. So if you kind of look at this architecture right here, you can see that all we did was look through 4 patterns. I mean, the channel monitor is a small one, so 5, okay. But all we've done is look through 4 main patterns, and we have completely a reactive architecture that will pretty much handle any kind of error. That's what I mean about reactive architecture. That's what it means to be reactive. All right, fantastic. So those are only kind of 5 out of probably a dozen patterns or so, but those are the core main ones, because as the last slide I showed you really has all of those put together in terms of a system that all those errors I just showed you, we can handle. And we can do it in Java without any specialized tools. Now that's where you can certainly, it makes it easier to code, let me put it that way, when you're using languages like Elm, for example, or Scala, or Akka Framework, or Play, or any of these. It makes it easier to code this. But the point is they're not required, but they're really fun to use. So, anyways, I hope that that kind of gave you a flavor for what reactive architecture really means, what it's about, some of the main patterns of reactive architecture, and the fact that this is pretty easy coding. I mean, this was not any heavy lifting at all. You've got all the source code. Just go to my GitHub repository and take a look at it. You can actually run it. It takes about 15 minutes to get it up and running, just to rerun the same demos I did. But anyways, hopefully that was informative and gave you kind of a good feel for being more reactive in the way we construct our systems. So, anyways, thank you very much. It was awesome speaking to all of you here. So thanks for coming out. And I think there's, Matt, you have some stuff to talk about, right?
No, just to say goodbye, Dave.
Oh, right. I'll give that. Awesome. Thank you all for coming.
If you are looking to drink, there is a bar called Stocks and Blondes a few blocks away that's open pretty late. Otherwise, have a good night, everybody.
Great. All right.
Hey everyone, we have a drawing real quickly. We have a few things to give away. You have a few minutes.
There you go.
Oh, wait a minute.
How do you get into the drawing?